All right, welcome back. We're now gonna start discussing data part design principles, right? We looked at finite state machines as one of the starting building blocks for how to do design, and now we need to look at the actual data path. And as the first topic, as part of the series, we're gonna look at pipelining. Okay. So, at a very high level, pipelining is probably something you have seen before with CPUs when you execute instructions sort of in a back to back fashion. We will sort of revisit that very briefly so that we all are on the same page in terms of what pipelining can do for us, what are the trade offs, what are the benefits that we get out of it, right? Once we understand how this works for processors, we can then start defining terms that are processor centric that can then help us understand corresponding terms for hardware, right? So the core objective of this lecture is to look at arbitrary data paths, to reason about how to pipeline them, what are the performance impacts of doing that, what are the cost concerns that we must be worried about, right? And then finally, we will look at how to describe pipelines in Verilog, how to reason about waveforms when you're looking at pipelined computations. And then finally, we will touch upon a topic that uh, connects pipelining to sort of this physical emerging property that data movement is sort of the biggest concern that we have. So what we need to start thinking about is pipelining wires, pipelining these long distance structures, and allowing high performance outcomes, even if you have these gigantic chips where you have to send data over longer and longer distances. Okay. So, looking at pipelining, we need to sort of revisit some of the early days of industrial manufacturing, right? So, pipelining is a term that comes from, sort of industrial manufacturing where you are trying to mass produce a product, and that to mass produce that, you need to create sort of this assembly line, right? Assembly line, a pipeline of specialized components, specialized machines, give specialized training to workers who are then going to contribute to the final product in sort of an incremental fashion, right? So that's sort of how sort of this whole idea of pipelining came into be. And so the underlying principle is, yeah, you have different stages that are working on individual tasks, right? You don't have one general purpose worker or one general purpose machine that builds the entire product. You can incrementally build it, and then you can train different workers for that subspecialization. So they don't have to be trained on the entire design process. They can focus on that one particular piece, right? So at this point, maybe it's worthwhile asking an open-ended question about whether you think this is a positive outcome or a negative outcome. That we've moved into a world, even in software design, even in hardware design, that different engineers are trained only in certain specific tasks, right? So there might be managers who have an overall perspective of how everything fits together, but the foot soldiers of the engineering firms are now extremely specialized. Um, so let's do a quick debate, right? What do you think? Is it good or is it bad that we have specialization? Okay. So in my opinion, it's bad, right? So you want to have a big picture view of how everything fits together. So one of the things you might want to consider doing is trying out different roles in the different co-ops that you might get a chance to do in the future. So you get this sort of complete picture of how different roles are going to work together, what sort of experience you need to be able to see how things fit together, right? If you're specialized, it becomes a little tricky to stay specialized only in that domain. So the alternative, if you don't want to generalize, is to at least be prepared to retrain yourself periodically, right? So be excited about new things so that you don't get locked into that one particular role, and you can, if required, move to a different role. You can change your job, go work for a different company that pays you better, treats you better, whatever the case might be, right? So it's an interesting sort of trade-off you need to consider in design in the design process. For our sake, in hardware design, pipelining is very useful, very important to get sort of high throughput behavior, right? High throughput here means the ability to consume multiple items of data continuously at a certain rate, and the more items you can consume and perform computation in pipeline fashion, the better the outcome is going to be. So one classic example of this is the NVIDIA GPU, which are not quite optimized for latency, right? So you're not going to get one answer quickly, but you're going to get a bunch of answers in a certain slightly slower amount of time. But because that bunch is a very large number, you effectively get very high throughput, so you can keep your hardware busy. You can get a lot of problems solved in that setup. Okay. So yeah, here's sort of a picture of the Model T assembly line. This is one of the first industrial places to use this sort of pipelined computation. Different workers would contribute different pieces to the assembly line, and then finally you would have this product, right? This car. Quick side note of history: there is an old Ford factory very close to where I'm staying in Singapore, and it was the site of the World War II surrender between the British and the Japanese troops. So there's just a quick diversion, right? You have this sort of nice connection between something that you're seeing on the slide and maybe something that you see in your neighborhood. Okay. A more modern example is that of electronics manufacturing, right? So countries like China, Vietnam, Taiwan, Korea, Japan, they've sort of mastered the art of producing electronic devices, and they do so by extreme specialization as well, right? So not only are their manufacturing processes advanced, but they have the workforce, the trained workforce that can operate on this and give us electronic devices that we all love, right? So now there is sort of this ethical dilemma, whether we are doing the right thing in sort of an overall context of the welfare of these workers. But this is the future that we have chosen, and that we need to hold these companies to account to make sure that they are doing the right thing for their workers as well as their customers. All right, so enough of that moralistic lessons. Let's move on to understanding how processor pipelines work, right? That's our first step here. So remember when you compiled C code, you produced a sequence of instructions that's going to run on your hardware, and then your hardware is going to operate on these instructions one by one. Right? It's going to operate on them in sequence. So each of the CPU sort of instruction execution flows consists of essentially 5 steps. There might be more steps for more advanced processors, but you have to get the instruction, fetch it, you have to decode it, understand what it's trying to ask you to do, execute it. Once it's executed, you need to account for any kind of memory operations you might be doing, and then there is a write back cycle as well to help you flush the results back to the memory locations that you want, right? So the way this would normally work on a well-engineered CPU is in a pipeline fashion, right? What I mean by that is you can overlap each of the 5 stages with each other, right? So I could be fetching an instruction for instruction A while decoding it for instruction B while executing for instruction C, and so on and so forth, right? So that allows me to keep all these 5 stages of my pipeline CPU busy with useful work. But I do have to worry about one thing, and that is dependencies, right? I can only execute a subsequent instruction if I have all the inputs I want to process that particular instruction, right? So processors have guards and checks in place to ensure that correctness or sequential ordering is maintained. So instructions won't be issued if the previous instruction is producing an output that is needed by this particular instruction. Right, so the safest way to do that is to not pipeline the CPU, right? That guarantees dependencies are obeyed. So here's an example of an unpipelined CPU, right? I'm doing fetch, decode, execute, memory, and write back all sort of in this one atomic step. And then if I want to execute a new instruction, I have to wait for the first instruction to completely finish before I can go back and issue that new instruction, right? And you can imagine that as I start stacking instructions, this is going to slow things down a lot. You're going to have extremely poor performance, but you're going to ensure that dependencies are obeyed, right? And it's not all bad, because sometimes you do want sort of deterministic output. You want to be able to predict how many cycles a certain computation takes, and maybe some non-deterministic effects could sort of slow things down, might give you better performance. But if you can't predict or analyze perfectly, that might be a problem, right? So a very simple unpipelined CPU would just serialize the execution entirely. Now, a more modern CPU that uses pipelining techniques is going to allow you to issue instructions back to back, right? Now, if this is a sort of a silly CPU, what you will notice is that it's going to issue instructions sort of immediately back to back, and not worry about dependencies, right? So we'll revisit that later and see why we need to worry about dependencies. But the most important thing to take away here is the fact that you are able to perform this sort of overlapped execution of different instructions in the hardware by using different parts of the CPU pipeline for different instructions, right? So for instance, at the beginning, you're only doing fetch for the first instruction and nothing else for other instructions. In the second cycle, you're doing fetch for the second instruction while you've moved on to decode for the first instruction. In the third cycle, you're doing fetch for the third instruction, decode for the second instruction, execute for the third instruction, sorry, the first instruction, and so on and so forth. So you can keep pushing data through your pipelines and keep every stage busy, right? You can keep every stage busy, but at any given point in time, you'll have multiple sort of partial executions of different instructions flowing through your pipeline, right? If you take a snapshot of the pipeline at a given point in time, this will be sort of staggered across different instructions. Okay. So what do we get out of this, right? So number one, we are able to make sure that the clock frequency that we are running our chip is quite high, and we will see why that is the case shortly. But sort of a high level explanation is that in one cycle you're only doing fetch or execute or decode and so on and so forth. You're not doing everything in a single cycle. So that cycle period definition can be shrunk to accommodate the worst case stage, right? The consequent outcome is that you get higher throughput in terms of how many instructions are retired, how many instructions finish executing. And this is measured in terms of metrics like IPC, instructions per cycle, or CPI, clock cycles per instruction, sort of the inverse of each other. And this doesn't come free. You do have to spend resources, registers, and control logic to be able to use pipelining. So it's going to cost you in terms of area and power. But in most cases, in I would say 99.99% of the cases, this is what you want to do, right? Now, what CPUs do that's really interesting is what happens when there is a dependency, right? So when there is a dependency between consecutive instructions, you have to do what is known as stalling a pipeline, right? A pipeline stall sort of forces an empty or a bubble or an idle slot to be inserted into the pipeline while the rest of the data is flushed out, right? So what's already in the pipeline continues, but nothing new enters the pipeline, right? And you continue the stall until you have what you need to start to resume computation, right? So usually this means that you're waiting for dependent instructions to finish, and once they are ready, once the results are ready, you can resume, right? So the stall can be withdrawn once all the dependencies are obeyed. Okay, so when you look at how sort of this instruction flow would work, if I compile my polynomial software code to assembly, I would see that I have maybe a series of 3 multiply instructions to compute ax square at the beginning, and then I'm gonna have I have to add b and add c and do those sorts of operations on top. And when I try to look at this in the time axis, if I want to get the correct answer, I have to make sure that I stagger my instructions. Okay, so let's walk through how dependencies will get enforced. So in the very first step, I'm going to issue the AX instruction. Okay, so I'm going to issue the AX instruction, and I'm going to write this back to the register T1 in this scenario. Okay, so once I've done AX, I can move on to computing BX, right? So now BX does not depend on AX, so I don't have to perform any stalls. I can issue these instructions right away, okay? But now let's say I want to do AX square. To do AX square, I need the result of AX, right? And I can only get that if I insert a bubble in the pipeline that delays the execution accordingly until I'm able to wait to get R1. And sometimes you may have data forwarding logic that might give you the answer a cycle earlier, but we're going to assume that that doesn't exist for now, right? So this T1 is then made available from the write back stage to the execute stage of the subsequent pipeline, subsequent instruction. Notice that you still had to grab the instruction to know that there may be a dependency, right? So unless you read the instruction, you don't know what's going on, okay? So that's going to insert that empty square, empty bubble into the pipeline. So now you have AX square and BX, and now I want to add them together. Now in this scenario, to perform this add, I have to wait for both AX square and BX to be ready before I can sum them up. So when I issue the fourth instruction, I now have to insert 2 idle cycles into my pipeline. Okay, so that will let me add ex square plus bx. And then finally, when I want to add c, again, I would need to add 2 extra idle cycles in that last instruction before I'm able to get the final result out. Okay, so notice, right, you're sort of delaying the execution of subsequent instructions if they depend on the sort of the result of a prior instruction. Now, as I said, there are certain forwarding structures you can put in place to maybe save a cycle here and there. You can also rearrange the instructions, right? For example, you might be able to factor things out, right? You can do ax plus b first, then multiply that by x, and then add c. But what you would notice is that that creates a strict sequential dependency, right? So I have to wait for ax to finish before I can add b, and I have to wait for that sum to be done before I can multiply it by x, and so on and so forth. So maybe I'll leave it as a homework assignment for you to decide whether or not factoring it gives you a better outcome in the end. Okay, so when you have a pipeline CPU, you are able to keep the different hardware operators busy to the extent possible. You're going to have stalls or bubbles in the pipeline. If the hardware detects that there is some kind of a dependency, dependency checking in itself is a fascinating area of research, fascinating area of design. When you're trying to use sort of simplistic hardware structures, if you have simplistic hardware structures, you do what is known as in-order processing. You're only executing instructions one after another, and all you need to do is every new instruction that gets read from the instruction memory, you check the previous k instructions depending on the depth of the pipeline, see if the input depends on any of those instructions, right? And that can be done by tracking the register uh, the register names that you write to and you read from, and if there is a dependency, you will know that right away. Now, more modern processors use what is known as out-of-order processing, which means they are fetching multiple instructions and they are allowing those instructions to be reordered. So the fact that bx happens after ax need not stop bx from executing before ax, right? So out-of-order processing lets that be the case, but it significantly complicates this sort of dependency tracking because they're executing instructions out of order. You now need to know exactly how many things are in flight, right? So if, for instance, if I have m things that I can issue in parallel out of order, and the depth of the pipeline is k, at most I will have m times k possible instructions in flight that may create dependencies with the m new instructions that have been fetched, right? So this sort of hardware can be quite expensive, and it is expensive, which is why out-of-order processors take significantly more resources than in-order processors, because you have to build this whole hardware circuit that tracks who depends on whom. There are lots of clever tricks for doing that, but it is something that's expensive. In the early days of the cell phone revolution, you had mostly in-order CPUs, in-order ARM processors. They slowly migrated to out-of-order because all of us really wanted fast performance. We really needed to tweet very, very quickly, and we couldn't wait those few extra nanoseconds it would have taken, and we would have gotten a more energy efficient CPU in exchange. But here we are, okay, with out-of-order processors. Now, when you're designing your own data path, you have to worry about these dependencies. Luckily, right, the reason a hardware design is a bit easier than processor dependency tracking hardware design is your data path is something that you're in control of, right? So your data path, you know upfront what dependencies are going to be there. You can plan for those dependencies, and we will see how to plan for those dependencies with pipelining. So you don't need this extra hardware that tracks dependencies because you've done all the thinking on the whiteboard, right? You've done all the thinking during the design stage. So when you are trying to deploy your hardware, trying to fabricate a silicon, trying to push out an FPGA bit stream, all of those pipelining effects have been considered. All of the dependency effects have been considered. Right? So that's a positive advantage for us when we're designing our own hardware. Okay, so let's sort of revisit the metrics IPC and CPI and apply that to a couple of examples to see how they might evolve, right? So we need two things to be able to compute this. We need to know how many instructions we executed. We also need to know how many cycles it took to execute all of those instructions, right? IPC is just instructions divided by cycles. CPI is the inverse of that. So both of these terms are used interchangeably in sort of industrial literature. For unpipelined CPUs, the number of clock cycles you're going to need per instruction is the depth of that pipeline, right? So you are not allowing the next instruction to execute. So you have to wait a certain number of cycles, which is going to be the number of stages in your pipeline, right? The advantage here is that no matter what code you execute, the CPI is going to be the same, right? Dependencies are irrelevant because you're not going to need to wait anyway because you're going to be executing instructions back to back, waiting, fully waiting the entire pipeline depth before starting the next instruction, right? Now for pipeline CPUs, the ideal case is you're able to pack instructions back to back into your hardware, right? That you don't have to wait at all, you have no stalls, right? So that's sort of an upper bound of how fast things can be, right? So the IPC or CPI here is going to be 1. That's sort of the best case behavior. And then depending on what problem you're trying to solve, you might get deviations from this idea, okay? So in sort of non-ideal cases, your IPC in the worst case is going to be 1 over k, where k is depth of the pipeline. Best case is going to be 1, and in general, it's going to be between that. And well-engineered, optimized programs will try to be closer to this ideal case of 1. Okay, so let's look at the IPC and CPI for an unpipelined CPU, right? So let's say you're executing k instructions for a 5-stage pipeline. You'll need 5k cycles, k instructions. So IPC is going to be 1 over 5, CPI is going to be 5. Again, this is slow, but it's a predictable outcome. Okay. So now when you have a pipeline CPU, you have these dependencies, and the exact nature of dependencies is going to vary with the problem you're going to solve. So for poly, we can count that it's taken us 14 cycles to do that entire operation. We needed to execute 5 instructions. So IPC is 5 over 14, CPI is 14 over 5. Design is faster, but the IPC is going to vary with the application. So you need to keep recalculating this number for different workloads, and there's no one magic right answer for IPC. It's very tied to the application you will run. So to sort of summarize, right, we covered the effect of pipelining on processors, right? The more pipeline stages you add, the more sort of registers you need to insert into your circuits is going to cost you more. It's going to increase latency, which is a term we will shortly define, which is number of cycles from input to output. You're going to get more throughput, again a term we will shortly define, which is how many instructions can you consume per cycle. You're going to need a smaller clock period, right? So which means your clock frequency can be higher because you're doing less and less work in a single stage. And finally, we know that registers are going to cost us area as well. Okay, so one sort of extreme thought experiment to consider is how much to pipeline. Right, we can keep pipelining, we can keep dividing work into smaller and smaller more cells until eventually you will notice that it doesn't give us continued benefits, right? So there is going to be sort of this Goldilocks idea where you get the most bang for the buck without spending too much hardware and without getting some minuscule improvements over the previous design, right? So the challenge with pipelining with RTL engineering is to find what that best spot is going to be for your design. Okay, so when you're designing your own data path, right, let's say you're designing ax square plus bx plus c, you can choose how to slice and dice this in a manner that makes sense for your target requirements, right? So I can have anywhere between 1 to 4 stages of pipelines, and we'll look at all of these examples soon. You will notice that each of these pipeline stages have a lot of variation in terms of cost, in terms of latency, in terms of throughput, and in terms of clock period. And that's hopefully help us understand and explain how all of these things are going to work. Okay. Now we're going to assume that all inputs arrive at the same time. Sometimes we can take advantage of delayed inputs, but we're going to assume that everything is given to us at the same time. We're going to use a very simple notation for pipelining, right? So when we draw these circuits, we're going to assume that inputs come from the left. All the inputs can be stacked on top of each other on the left. All the outputs are going to leave on the right. And then the different pipeline stages will be indicated by these dotted lines. And inside a pair of these dotted lines, you're going to pack your arithmetic or logical operation. And then you can move these, you can slide these pipeline stages around until you find sort of the best result that you want for your application. Okay. Now, another thing to remember is every time one of these edges crosses a dotted line, one of these dependencies crosses a dotted line, you need to plop down a register, right? You need to add that register because it is what is going to allow you to run the pipeline at a given rate. Okay, and we'll revisit this. So this sort of uh, extensive register additions is what makes pipelining work. You're going to have to extensively add registers throughout your hardware at the right places and control them in the right way to get coordinated data movement forward. Okay. So what we'll now do is we will define some of the terms that we will be encountering when we investigate different circuit trade-offs, right? So number one is throughput. We're going to define throughput as the rate at which we consume inputs, right? And it's going to be a number between 1 and a fraction less than 1. A number, if the number is 1, it means you're consuming an input every cycle. Okay, so that's sort of the ideal case, sort of IPC of 1. Okay, if you consume an input every 2 cycles, throughput is 1 over 2, and so on and so forth. Right? You can have a rational P over Q sort of throughput, and that's going to depend on how many inputs you can consume per cycle. Right? If you have a purely combinational circuit with no pipelining, throughput is not defined because you don't know what is the safe time to change your inputs, right? So you can only assume that things are stable and that if you must change the inputs, you need at least one stage of pipeline somewhere, okay? So just to summarize, throughput is the rate at which you are able to consume inputs, and ideally you want a rate of 1, okay? Now, correspondingly, latency is the number of cycles between the time an item of data enters your circuit and the time data leaves the circuit. The unit of measure here is cycles. You're counting how many cycles it takes for input to arrive and output to leave, and it's sort of this end-to-end latency of data propagation. Ideally, you want a single stage pipeline. Right? You just want one stage because that gives you the answer right away and you can move on and do other things. But if you want high throughput and high performance, you're going to have to extensively pipeline, which means one of the things you do have to often sacrifice is latency. You have to allow your circuit to take several cycles before you get the result out. Okay. Again, for combinational circuits, there is no latency. It's defined as 0. Okay. Now, in tandem with throughput and latency, we have to understand one more term, and that is clock period, which is the width of the clock pulse, the time separation between two positive edges, for instance. Okay. If you want a faster clock frequency, you want the separation between the clock edges to be as small as possible. Okay. So as you keep pipelining more and more, you're doing less and less work in each pipeline stage. So you can start shrinking your clock period. You know, there's a rule how you can do it. You can't just arbitrarily reduce clock period. You have to obey the work specification that's happening inside that particular pipeline stage. All right, so we're now going to look at an example of pipelining a circuit, and we're going to start off with a factored version of poly, right? So what we're going to do here is we're going to compute ax plus b, multiply that by x and add c to it, and we're going to do this in a fully pipeline fashion. So how are we going to do this? So the first rule of pipelining that we're going to obey is we're going to pipeline the input and the output ports, right? So what I mean by that is as soon as data enters the circuit, the first thing it does is it pipelines itself. And as soon as data needs to leave a circuit, again, it pipelines itself on the way out. This is just like brushing your teeth both in the morning and at night. I hope everyone's doing that for the safety and sanity of your own dental hygiene. We have to obey the same sort of pipelining hygiene inside a digital circuit. Okay. So now that we've pipelined inputs and outputs, what I've also done is I've pipelined the result of every single operation. I've pipelined the output of multiply, I've pipelined the adds, and so on and so forth. So this is going to give me the highest possible frequency because the work I am doing in every single pipeline stage is the smallest possible. Okay. Now let's look at the always block that implements this circuit. Okay, so there are a couple of things to tease out here. So number one, you notice that I have a whole lot of signals flowing around here. And the reason for that is I need to account for the times every single time an edge crosses a pipeline dotted line, I need to put in a register there. So for example, I know that X is going to cross these two pipeline lines, so I need to insert registers at those places. C is going to cross these three pipeline lines, and I need to place a register at all of those places. So it's going to create lots of these intermediate signals, and to keep a handle on all of this, what I use for my terminology is any signal I have that is combinational, I attach an underscore C to it. Any signal I have that is registered, I attach an underscore R suffix to it. And depending on the depth of the pipeline, it can be R1, R2, and so on and so forth. So it keeps a bundle of signals sort of coherent, so I know what set of signals I need to use for a given particular operation. Okay, so let's go step by step and look at what code corresponds to what computations in my pipeline. Let's look at what I see here as stage 1. Okay, so in stage 1, I am doing A times X. Notice I am using A underscore R and X underscore R, which have been registered in a separate always block when things come in. And these input signals are further pipelined one more time. So notice that I am pipelining X, B, and C one more time to create the R1 versions of those signals. So what does this mean in the hardware picture, right? So this multiplication obviously is this particular operation, right? There's no surprises here. But X underscore R1 is going to be this particular register here. B underscore R1 is going to be this particular register here. And C underscore R1 is going to be this particular register here. So the job of the RTL block for the first stage is essentially to take all of this slice, this whole thing, and implement it here. Okay. So one chunk of stage 1 code is responsible for one vertical slice through your hardware, and sort of the same thing happens going forward as well, right? So if I now look at, let's say stage 2, I am going to do an add, right? So the add here corresponds to the add here, and I have 2 extra pipelines to account for. That is X underscore R1 here and C underscore R1 here. Notice I don't have to pipeline B anymore because the lifetime of B stopped at this operation. I don't need to use B downstream in any of my computations. So you only pipeline signals for just enough distance. You don't need to do it for the entire pipeline depth. Okay, and now sort of similar sort of behavior applies to stage 3 and to stage 4. So I'm not going to go through that, but you're going to see that these vertical slices correspond to these chunks of Verilog code. And at every stage, sometimes you have to just copy signals over by an extra cycle to ensure that at any given stage in the pipeline, you're seeing consistent, coherent inputs. Okay. Now, I can draw each of these stages as these individual blocks correspond to that dotted line. And then the more of these chunks I have, the more pipeline stages I have in my computation. Now, I can choose not to pipeline so extensively, right? I can choose a slightly less aggressive pipelining strategy. And now I can do the add and multiply for AX plus B in the first stage. And I can do the result of that in the second stage, right? So I can take that result, EX plus C, and do that in the second stage. So now you notice there are fewer vertical lines. You still have your input and output pipelines as before because you still need to brush your teeth in morning and evening. But in the middle, you only have this one pipeline stage. Okay. So again, if we look at our code here, our stage 1 code is going to do EX plus B, right? This whole operation in that one line of code, right? So that whole one line of code is going to produce Y1, which is your result. And that's going to be this chunk of registers here, right? So this Y1 is going to correspond to this chunk of registers here. And then in stage 2, all you have is this second set of multiplies and adds. So you are doing these 2 sets of multiplies and adds. And then the output Y is going to be this chunk of registers here. Okay. So now you only have 2 stages. So less Verilog code to write. More work in an individual stage, so we are going to sacrifice some performance, and what we get is these 2 blocks of code correspond to these 2 stages of pipelining. All right, and finally we can choose not to pipeline internally at all. We can do the whole AX square plus BX plus C computation in one shot. Again, you still need your input and output pipeline stages for the same hygiene reasons as before, and then all you see is this one line, one non-blocking assignment that performs EX plus B multiplied by X plus C. And then, yeah, so this signal Y is going to correspond to this register here. And that's it. That's all you get, right? So you're looking at an example where you are varying the number of pipeline stages. You are You see the effect this has on the kind of Verilog code you need to write. The only sort of tricky thing here is you need to ensure that you are uh, pipelining signals to the correct depth before you consume them, right? So the X, B, and C signals have to be pipelined accordingly to varying depths depending on how deep your pipelines are, and then you have to use them at the correct moment in time, right? You can't just go back to B or inputs and just pick those directly without pipelining them accordingly. Okay, hopefully this was relatively clear. And now we're going to look at a timing diagram of this example. Okay, so this is a little tedious, so you have to walk through cycle by cycle, right? So as before, we're going to start off by drawing our clock and reset signals at the top. These clock and reset signals are going to be sort of coordinated. So in the first clock cycle, reset is 1. So you can assume that all the intermediate values are going to be 0 at that point in time, because that's how we've reset them here in this block of code. And in the second clock cycle, you notice that reset will be sensed as 0. So at this point in time, I can go ahead and start executing this code. So I'm going to execute this code every single cycle. Okay. So in the very first cycle, what we're going to compute is essentially y0, right? And the reason we're going to compute y0 here is because this is going to consume AR and XR to compute the correct result y. So what's going to happen at that cycle? I'm going to sample the value of AR. I'm going to sample the value of XR to compute a new value of y0. Okay. Now B, C, and X will just be pipelined, so you will get the same sort of sampled values delayed by one cycle. And this is all you have to do in this first stage. Okay. Now at that stage, even though I'm going to execute the code for y1, y2, and y, because the inputs generally change, I don't have to account for them at all. Okay. So what we will essentially see is that by sampling the value of a and x, I'm able to compute y, and by sampling the values of b, c, and x, I can compute the _r1 versions of these signals. Now in the second cycle, right? So in the following cycle, right? In this cycle here, I'm going to re-execute my always block. At this point, y0, b_r1, c_r1, and x_r1 will not change because those inputs in this case have not changed. What will change though is y0 and the r1 versions of b, c, and x, right? So which means I can go ahead and compute y0 plus b, and I'm going to sample y0 and b at that clock edge, and just after the clock edge, y1 is going to change its value. And then as before, I'm going to take c and x and just delay them by one extra cycle. Okay. Now in the following clock cycle, which is going to be this clock cycle, I'm going to sample the value of y1 and xr2, and I'm going to, y1 and xr2, and I'm going to move them to y2. And then finally, I'm going to pipeline c1 extra time. And in the very last cycle, I'm going to do y2 plus cr3, and that gives me the final result, right? So what you saw was a sequence of pipeline stages step by step that helped me get the final result I wanted. Okay, we can do the same sort of thing for just the two pipeline stages. And for these two pipeline stages, what you'll see is at the beginning, I'm going to compute ax plus b. That gives me y1 after the first clock edge. And I'm just going to copy the values of x and c once. And in the second cycle, I'm going to compute y1 times xr1 plus cr1, which is going to finally give me the value of y. Okay. Okay, and for a single stage design, I can simply just compute ax squared plus bx plus c and be done with it in that one cycle. Okay, this is the simplest pipeline waveform diagram. But as we will see, there's a cost performance trade-off. So let's now revisit that first example where we extensively pipelined the entire hardware, right? So what we now need to do is start plugging in values for latency, throughput, cost, and clock period, okay? So number one, we're going to start counting latency, right? To count latency, I'm going to annotate each stage by a number, 1, 2, 3, 4, 5. So I count how many vertical lines I have, and that is my latency, okay? The throughput in this case is 1 because I can push in a new value every clock cycle. Okay. To measure cost, I'm going to measure cost in terms of the number of registers I need, and I'm going to measure them level by level, right? So first I need 8 registers for X, 8 registers for A, 8 for B, and 8 for C, right? So that's sort of this term here. Notice that I counted only 8-bit registers for it, because what I'm able to do in hardware is I can take this signal and I can perform the fan out at this stage, right? So if the same signal crosses a pipeline stage multiple times, you don't need to count the same signal twice, because the distribution can happen in the next stage, right? There is no difference whether you factor it out earlier or afterwards. The fan out is still going to work just as fine. So might as well pick the cheaper option with fewer registers. Now for the second stage, I have to pipeline X, A, B, and C. Now I have to be a little careful about how many bits I need, right? So for X, I need 8 bits. For the product here, I need 16 bits. B and C are 8 bits again, and that gives me this term here, okay? In the following cycle, I need to again pipeline X and pipeline Y1 and pipeline C. So I get these 3 terms here. And notice that for the add, I didn't have to apply the addition rule of plus 1 bit, because I know that A times X is not going to be the largest possible number. Okay. And then finally, I am going to count these 2 stages, Y2 and Y. I have to also count C2 here. And this will give me the 24 plus 8 signal. So now I know that this is 16-bit input. This is an 8-bit input. So my result here is going to be 24-bit. And same here as well. Okay. So I'll end up with this entire expression that is going to be the sum of number of registers I have. I went stage by stage. I calculated how many bits each of these signals takes. I have to apply my multiply add rules with some caution, and then I get my overall register cost here. Okay. Now clock period calculation is super straightforward. All you have to do is find the worst case of all the stages, right? So clock period is always going to be the max of every single stage, right? So in this case, it's going to be a combination of the first multiply, the first add, the second multiply, the second add, and the worst of that is going to be your clock period. So for instance, let's plug in some numbers here, right? For instance, the first multiplier was 10 nanoseconds, the first adder was 5 nanosecond, the second multiplier, because it is a 24-bit multiplier, let's say it's 15 nanoseconds, and then this last adder is, let's say, 6 nanoseconds, right? Clearly, this is the slowest stage, and what this forces you to do is operate at the frequency of the slowest stage, right? The clock period has to be adjusted to be wide enough to account for that slowest operation of computation, right? Okay, so this makes sense. Now we can move on to the next step. So in this case, you only have that one intermediate stage. So the latency here is going to be 3. I can count 1, 2, 3. Latency is 3. Throughput again is 1, because I can do push one set of inputs every cycle. Cost again is going to be computed similarly. You're going to account for 8 for X, 8 for B, 8 for C, 8 for B. So that's these 4 stages. Then I only need to pipeline X and Y1, right? So at this point, and C, sorry. So at this point, I need to add these 3 signals here. Notice at this point, I did not have to worry about this signal or this signal again, right? Which is what I needed for the previous example. And then finally, I only need this 24-bit result to be added at the very end. So I get a reduction in the number of registers required to do this, okay? Now, obviously, I'm going to lose something here. What I'm going to lose here is clock frequency. My clock period is going to be more than before, right? So I need to add up each stage. I need to add up the time required for doing both the adds and multiplies. And if we use the numbers from the previous slide, I believe it was 10 nanoseconds, 5 nanoseconds, 15 nanoseconds, and 6 nanoseconds. So this will give us 21 nanoseconds and 15 nanoseconds. So obviously this is going to be the 21 nanosecond period that we have. So it's much more than the 15 nanosecond we saw earlier. So this circuit is going to operate significantly slower than the previous one, right? So you're doing a trade-off, you're getting something in exchange for sacrificing something else. Okay, and then finally, when you only have the input and output pipeline stages, right? As you'll notice, you only have 2 stages, so you have a latency of 2. Throughput still stays 1 because you're still able to push one new item of computation every cycle. When counting registers, again, I'm going to count 8 registers here, 8 here, 8 here, 8 here to get this first term. And then I only have this 24-bit signal here. So my register cost is now significantly cheaper than the previous examples. Unfortunately, my clock period is the sum of every single stage, right? So it's going to be 10 plus 5 plus 15 plus 6. That's going to be 36 nanoseconds, right? So you ended up with a significantly slower clock period here, and you ended up saving a lot of registers, but in most cases, you are more than willing to sacrifice registers to get higher clock frequency. So these are the sort of trade-offs you need to make. Now, one thing to note is that throughput did not change. Throughput is still 1. You're still able to do one item every cycle. Sometimes that can be tricky if I partially pipeline some signals. So there'll be a tutorial example that covers this case where throughput is not 1 and you have to be able to detect when that happens. Okay, so let's now move on to doing wire pipelining, right? So initially I alluded to the fact that data movement inside the chip is increasingly expensive. So most of the delay that you're going to notice when you start doing timing analysis and design optimization is going to be in the wires and not these adders and multipliers, right? So for concreteness sake, if you look at a modern FPGA, you will see that a lookup table takes 0.1, 0.2, 0.3 nanoseconds, whereas the delay between the locations of those lookup tables, the wire that you need to move that data, can be 1 to 2 nanoseconds, right? Almost an order of magnitude more delay in the wires, and this is just getting worse and worse, right? So you really need to get a handle on wire pipelining, which is what you need to do to tackle that wire delay here, okay? So we need to extend the idea of pipelining to not just multipliers and adders, but to also do it for wires. So in this case, what you see here is the same computation as before, but I have decided to place the first AX plus C computation in one side and the second multiply by X plus C computation on another side of the chip. So you have this gigantic sort of distance that you need to cover between the output of the first adder and the input of the second multiplier. And the way to attack this is to add pipeline stages along the length of the wire. Right, so you need to add these pipeline stages sort of geometrically distributed at equal lengths between the source and the destination. And what this does is it takes the wire and breaks it up into lots of these tiny chunks, right? And we will revisit how wire delay grows as a function of length later. But the clue that I'm going to give you is doubling the length of the wire makes wire delay grow faster than 2x. Right? If you do nothing to the wire, it's going to grow very aggressively, so the speed drops off dramatically the farther away things are. There are things you can do to the wire to make it high performance that we'll cover later. But even with that, one thing we need is to be able to partition those long wires into lots of smaller wire segments and then place a register along each of those segments. Okay, so you have equidistant pipelining across the wire length, and then your clock period is going to be defined by a bunch of components, not just the compute, but also the work that you're going to be doing in these individual stages. So you have to start defining terms like T-wire to be able to account for that. And if I look at the Verilog code for this, you will notice that there is this chunk of weird looking code where I am doing no arithmetic work, right? I am simply creating pipelined versions of wires. That's all I'm doing here, right? I'm simply creating pipelined versions of wires. I added these these sort of wire pipeline stages in Verilog by simply taking the same signal and creating R1, R2, R3 copies of that signal without doing any compute along those wires. And then the CAT tool, when it runs the synthesis, place and route, it has the freedom to use all these extra registers to stagger across the chip, right? So it will decide what the best place is going to be. The newest versions of Vivado and Cortex, the Xilinx and Intel FPGA tools, can use that freedom you give to the tool to distribute these registers exactly where they need to go. In some of the older tools, you had to do it manually. You needed to go and manually find the XY coordinate for these registers. that used to be very tedious, right? So now all of that's automated, and the tools do a fairly decent job of pipelining circuits, right? So what these tools tend to do is you need to know exactly where to place things, right? So uh, a lot of these decisions get made before you have any sort of physical knowledge of where things are going to end up. So you can start making sort of predictive assertions. You can make a prediction that, okay, this wire is going to be this long, and chances are it's going to need these many nanoseconds of delay. So let me place the register somewhere along this line, and then later on, once you see what's happening, some tools also give you a feedback option. So you can wait for the placement to happen, and you can use that to go back and say, okay, now that I know where things are, maybe let me physically relocate a register around. So that's sort of a retiming step. We'll cover retiming later, which can be done both in software and it can be done after placement is done, also in software. But it's something that can let you do this in an iterative fashion if required. Okay, so now this might seem fairly tedious. I have to go and start accounting for where the pipelines are going to be. One of the nice things about hardware design is a lot of CAD tool support exists for these commonly used features. So you could just add a set of registers at the output of a circuit and let the tool decide what's the best place to place it. So instead of you having to choose where to pipeline after the adder or after the multiplier, you let the tools decide. And that freedom is useful even at the physical side of things when you're placing or uh, splitting wires, so that the tools know what's the right thing to do once the things get placed on silicon. Okay. So now this problem has been around for a while, right? So if you look at the microcode of one of these Pentium 4 processors, you'll see that it has 2 cycles dedicated to waiting for signals to traverse the chip. So they're not doing any useful work, right? So number one, you have to wait. The processor has to literally wait and do nothing while signals merrily go across the chip. And second, you notice that this is not a 5-stage pipeline, right? What we saw earlier was a simple 5-stage pipeline. This is a 20-stage pipeline with lots of work that it needs to do. So modern processors are even more pipeline stages than this. And in contrast, you will also notice that modern Intel FPGAs have extensive pipelining in the fabric. So not only do you get pipeline registers explicitly, you can also get these implicit registers scattered throughout the fabric, and then you can choose to use them or not depending on where your delays are, right? So the wire pipelining component of FPGA design is now significantly cheaper with the new Intel HyperFlex FPGAs. Okay, so the last topic we will consider is how bubbles flow through a pipeline, right? So just like you can get bubbles in a water pipeline where you might have these sort of little pockets of air going through. You can have stalls in the pipeline that introduce junk data or no data at all into the pipeline, and all we need to do is make sure how it tracks and make sure to throw it away at the end, right? So as we saw in CPUs, bubbles are due to stalls. In data paths, bubbles may be due to a variety of factors, but for now we will consider that it's due to absence of input data, right? So a bubble is nothing but a null operation or a junk operation inside your hardware, and all you have to do is ignore it, right? So it doesn't matter what's being computed, you just have to throw away or discard that data. So the way we're going to do this is we're going to add a valid signal that piggybacks along with the pipeline, right? So if you want to indicate whether or not data is junk or not, we can use a valid indicator, and that valid or invalid indicator is going to tell us whether there is useful work or junk stuff in the pipeline. Okay, and the length of this valid signal is going to track the length of the pipeline. Right? You essentially have to replicate exactly what's going on in the pipeline on the valid signal here. So initially, let's say everything is valid, everything is flowing along nicely, and then at some point you decide to introduce a bubble, right? So a bubble is junk data, in this case on X. So my X valid goes 0 at this point in time in conjunction with X becoming junk. And then as the junk data propagates through the 4 stages, because X valid also suffered the exact same number of cycles of delay as the data, when junk value appears on Y, you have a way of indicating that it is junk. So Y valid will be junk at this point in time, right? So that gives you a sort of a certificate that this data is going to be good or bad, and you can choose to discard it downstream. And if I look at the pipeline sort of behavior here, I've taken the waveform from the previous example where I have A, B, C, and X, and as they propagate through the pipeline, you get Y after a certain amount of time. And here I have indicated X valid is 1 only for that one cycle. It's junked every other time. So what you see is as data propagates stage by stage, you get this sort of indicator that the output is valid at exactly the right point in time when the output changes. Right? So all you had to do was calibrate the latency of my valid wire to match the latency of my compute data part. Okay. So to wrap up, what we saw in today's lecture is that we can use pipelining, a concept borrowed from industrial manufacturing and a concept extensively used in CPUs. We can apply the same techniques to our own custom data paths. Unlike CPUs, we are in control. We can choose how many pipeline stages we want. We can choose how to manage dependencies. We already know what the dependencies are. So all we really have to do is delay certain signals by adding extra pipeline stages and using them in sort of a coherent, consistent fashion. We saw that in the end, modern chips suffer a lot of wire delays. So what we need to start doing is pipelining wires and keeping them pipelined at sort of equidistant steps along the wire, so you get useful work done, even if things are spread across the chip. Finally, we looked at a very quick example of bubbles. Bubbles in the pipeline indicate the presence of invalid data or junk data. And by creating a valid signal that mimics the flow of data through the pipeline, by making sure the valid signal sees the same number of pipeline stages, you're able to get consistent output at the end. Okay. So one thing I'll leave you with is a question whether you can pipeline any circuit. Is there a limit to how much you can pipeline, and are there classes of circuits which you cannot pipeline? Okay, so with that, we come to the end of this lecture.